Picture this. It's 3 a.m. at the Catalina Sky Survey in Arizona, and a computer algorithm has just flagged something unusual. A new dot of light, moving against the backdrop of stars, following a trajectory that brings it uncomfortably close to Earth's neighborhood. The automated system calculates an initial orbit, runs the numbers, and for a brief moment, shows a tiny probability of impact in the year 2032. This scenario plays out several times each year across observatories worldwide. Each new discovery triggers the same careful process of observation, calculation, and verification. Most of these objects turn out to be harmless space rocks that will pass Earth at safe distances. But that initial moment of uncertainty represents one of astronomy's most sobering responsibilities. The year 2032 holds no special astronomical significance, yet it appears frequently in asteroid tracking discussions. Why this particular year? The answer lies in how we discover and track near-Earth objects. When astronomers first spot an asteroid, they have only a few data points to work with, creating an uncertainty cone of possible trajectories. Sometimes, purely by chance, Earth's future position intersects with this uncertainty cone. The computer models flag a potential impact, assigning it a probability based on current data. These initial assessments often show alarming numbers, sometimes indicating impact chances of 1 in 100 or even higher. But here's the reassuring truth that asteroid experts know. Continued observations almost always eliminate these apparent threats. As telescopes gather more data points over weeks and months, the uncertainty cone narrows dramatically. What initially appeared to be a possible collision course becomes clearly defined as a safe passage. The current state of asteroid monitoring for 2032 is remarkably clear. NASA's Center for Near-Earth Object Studies maintains comprehensive catalogues of known asteroids, their orbits calculated with extraordinary precision. No object currently tracked poses any significant threat to Earth in 2032. The uncertainty cones for all known near-Earth asteroids exclude our planet entirely for that year. This certainty comes from decades of systematic sky surveys that have catalogued over 90% of potentially hazardous asteroids larger than 1 kilometer in diameter. These are the objects that could cause global catastrophe if they struck Earth. Smaller asteroids, while numerous and harder to detect, pose regional rather than existential threats. The question of whether an asteroid will hit Earth in 2032 has a definitive answer based on current knowledge. No known object poses such a threat. This conclusion rests on solid observational evidence and sophisticated orbital calculations that have transformed asteroid detection from lucky accidents into predictable science. Every 30 seconds, somewhere on Earth, a robotic telescope captures an image containing millions of stars. Within minutes, powerful computers compare this image to previous observations, hunting for the telltale sign of an asteroid, a point of light that has moved against the stellar background. This process, repeated thousands of times each night, forms the backbone of humanity's asteroid defense system. The Catalina Sky Survey in Arizona leads this global effort, operating 2 telescopes that together discover more asteroids than any other facility on Earth. Perched on Mount Lemmon at 9,000 feet elevation, these instruments spend clear nights systematically photographing the sky. Their computers process over 100,000 images annually, each one scrutinized by algorithms that can detect asteroid motion as subtle as a few arc-seconds per hour. But Catalina doesn't work alone. The Linear Project in New Mexico, operated by MIT Lincoln Laboratory, contributes discoveries using advanced CCD cameras originally developed for satellite tracking. NASA's NEOWISE mission, orbiting Earth aboard an infrared space telescope, specializes in finding dark asteroids that optical surveys might miss through their thermal emissions. The Pan-STARRS telescopes in Hawaii add crucial wide-field coverage, surveying enormous areas of sky in single exposures. Each telescope in this network has its own strengths, and together they create overlapping coverage that ensures few asteroids escape detection. Detection is just the beginning. Once a new asteroid appears in survey data, a complex international network springs into action. The Minor Planet Center at Harvard University serves as the global clearinghouse, collecting position measurements from observatories worldwide and calculating preliminary orbits within hours of discovery. This rapid response capability stems from decades of technological advancement. Modern CCD cameras detect objects millions of times fainter than human eyes can see. Automated data processing systems analyze thousands of images while astronomers sleep. Global communications networks ensure critical observations reach experts within minutes. Current surveys catalogue approximately 3,000 new near-Earth asteroids each year. The known population has grown from fewer than 1,000 objects in 1990 to over 34,000 today. This exponential increase reflects our dramatically improved ability to find these objects before they surprise us. Geographic distribution ensures continuous sky coverage as Earth rotates. When night falls over Arizona, dawn breaks over Australia's Siding Spring Observatory. European facilities fill additional gaps, creating a detection network that never sleeps. The reassuring reality is that this network works. No significant asteroid impacts have caught us completely unprepared since systematic surveys began. The Global Detection Network represents one of humanity's most successful international scientific collaborations, where countries unite in protecting Earth from cosmic threats. When astronomers discover a new asteroid, the first question isn't whether it might hit Earth, it's whether we have enough observations to calculate a meaningful orbit. With just 3 position measurements spread across a few nights, the mathematical uncertainty is enormous. The asteroid might follow any of thousands of possible trajectories, creating a probability cloud of potential future positions. Computer models take those early observations and project them forward in time, calculating where the asteroid might be years or decades in the future. They account for gravitational influences from the Sun, planets, and even large asteroids. The result is a 3-dimensional uncertainty region that often includes Earth's orbital path. The Torino scale, developed by MIT's Richard Binzel, provides a standardized way to communicate impact risks. This color-coded system ranks potential threats from 0 to 10, similar to hurricane categories. A rating of 0 indicates no threat, while 10 represents certain impact by a large object capable of causing global catastrophe. But here's the crucial part that media reports often miss. These initial risk assessments are based on extremely limited data. The mathematical models must account for enormous uncertainties, which often result in apparently alarming probability estimates. The probability calculations follow rigorous statistical methods. Astronomers run thousands of virtual orbits, each slightly different within the observational uncertainty. They count how many virtual asteroids intersect Earth's position at specific future dates. If 100 out of 100,000 virtual orbits show impact, the calculated probability is 1 in 1,000. As additional observations accumulate, something remarkable happens. The uncertainty cloud shrinks dramatically. What initially appeared as thousands possible trajectories narrows to a few dozen, then a handful, then a single well-defined path. The mathematics that initially suggested impact now reveal a safe passage. This process explains why asteroid threat announcements often seem to disappear from news coverage. The dramatic headlines about potential impacts give way to technical updates confirming safe passage. From a mathematical perspective, this outcome is virtually inevitable for the vast majority of discoveries. Modern orbit determination can predict asteroid positions centuries into the future, with uncertainties measured in kilometers. This accuracy stems from our detailed understanding of gravitational forces and sophisticated computational methods. For 2032 specifically, the mathematical analysis is comprehensive and reassuring. Every known near-Earth asteroid has been tracked through sufficient orbital arcs to eliminate significant uncertainties. The probability calculations show 0 meaningful risk from catalogued objects. December 19, 2004. Roy Tucker, David Tholen, and Fabrizio Bernardi were analyzing routine observations from Kitt Peak Observatory when they noticed something unusual. A faint point of light was moving slightly faster than typical for objects at that distance. They had discovered 99,942 Apophis, which would become the most famous near-Earth asteroid of the early 21st century. Named after the Egyptian god of chaos and destruction, Apophis quickly earned its fearsome designation. Initial orbital calculations placed it on a trajectory with a 1 in 37 chance of striking Earth on April 13, 2029. The numbers were sobering: impact by an object roughly 370 meters across, large enough to devastate an entire region. The discovery transformed asteroid impact risk from theoretical concern to immediate reality. Here was a specific object, following a precisely calculated orbit, that might actually hit our planet within the lifetime of people then living. News media worldwide ran stories about the doomsday asteroid, emphasizing the unlucky date of Friday the 13th. But Apophis became a perfect case study in how asteroid threat assessment works. As observatories worldwide turned telescopes toward this visitor, additional observations began refining its orbital path. Each new measurement reduced uncertainty, gradually shifting probability calculations. In December 2004, Apophis held a rating of 2 on the Torino scale. By late December, improved observations had raised this to level 4, an unprecedented rating indicating a close encounter meriting public attention. For a brief period, Apophis was the highest-rated asteroid threat in history. Then mathematical reality began working its reassuring magic. Additional observations in January 2005 slightly reduced the impact probability. More data in March further narrowed the uncertainty. By August 2005, observations had accumulated sufficient precision to rule out the 2029 impact entirely. The refined calculations revealed that Apophis would approach within 31,000 kilometers of Earth's surface on April 13, 2029. That's closer than our geostationary communications satellites, making it visible to the naked eye as a fast-moving star-like point. No asteroid of comparable size had approached so closely in recorded history. The Apophis encounter provided crucial lessons about asteroid detection and risk communication. It demonstrated that initial threat assessments, while mathematically valid, often overstate actual risks due to observational uncertainties. Most importantly, it revealed how additional observations rapidly eliminate apparent threats. Today, Apophis continues approaching its 2029 encounter, now classified as entirely safe. The asteroid that once represented humanity's worst nightmare has become an opportunity for unprecedented scientific study. For 2032, no object even remotely comparable to Apophis exists. Our catalogues contain no asteroid following a trajectory that could threaten Earth in that year. The fear that Apophis briefly inspired has given way to confidence in our ability to detect and assess cosmic threats. The difference between a spectacular fireworks show and global catastrophe comes down to size. An asteroid 10 meters across creates a brilliant meteor before burning up harmlessly in Earth's atmosphere. An asteroid 10 kilometers across ends civilizations. Understanding these size categories is crucial to grasping why astronomers can confidently state that 2032 poses no significant asteroid threat. At the smallest end, house-sized asteroids enter Earth's atmosphere daily. Most burn up completely at altitudes of 50 to 80 kilometers, creating shooting stars that delight sky gazers. These tiny visitors, typically 1 to 5 meters across, pose no threat except perhaps to an unlucky astronaut in their direct path. City block-scale asteroids between 10 and 50 meters across present more complex scenarios. The 2013 Chelyabinsk meteor, roughly 20 meters in diameter, represents a typical example. It exploded at 30 kilometers altitude, creating a shockwave that damaged buildings and injured over 1,000 people, but caused no deaths. The transition zone between 50 and 100 meters marks where asteroids begin surviving atmospheric passage to reach Earth's surface, largely intact. These objects can create craters hundreds of meters across and cause regional damage comparable to nuclear weapons. The 1908 Tunguska event likely involved an object in this size range. Stadium-sized asteroids, roughly 100 to 500 meters across, represent serious regional threats. An ocean impact could generate tsunamis affecting entire continental coastlines. A land impact would devastate an area the size of a small country. These objects occur roughly once every 10,000 years. The civilization-threatening category begins at approximately 1 kilometer in diameter. These mountain-sized objects possess enough kinetic energy to inject massive amounts of dust into the atmosphere, potentially triggering global climate change and agricultural collapse. The dinosaur killer category includes asteroids larger than 10 kilometers across. The Chicxulub impactor that contributed to dinosaur extinction 66 million years ago belongs to this category. Such impacts cause mass extinctions and fundamentally reshape Earth's biosphere. Current detection systems focus most heavily on civilization-threatening asteroids. NASA's congressional mandate requires cataloging 90% of near-Earth asteroids larger than 1 kilometer. This goal has been largely achieved, with surveys having found over 90% of these potential global threats. For 2032 specifically, the size analysis is particularly encouraging. All known asteroids large enough to cause global catastrophe have been tracked through complete orbital arcs that eliminate 2032 impact scenarios. Regional scale threats from smaller objects remain statistically possible but highly improbable. The detection bias toward larger objects actually works in humanity's favor. The most dangerous asteroids are also the easiest to find, meaning our catalogues preferentially include the objects capable of causing the worst damage. July 25, 2019. 3 days after a 100-meter asteroid passed between Earth and the Moon, astronomers at Australia's Siding Spring Observatory spotted it in their survey images. The object, designated 2019 OK, had approached within 65,000 kilometers of our planet, less than 1/5 the distance to the Moon. For a brief period, this city block-sized visitor was the closest known asteroid to pass Earth without impacting. The discovery of 2019 OK sent shockwaves through the asteroid tracking community, not because it posed any threat, but because it revealed gaps in our detection capabilities. Here was an object large enough to devastate a metropolitan area, and we found it only after it had safely passed by. 2019 OK possessed several characteristics that made it particularly difficult to detect. Its highly elliptical orbit brought it from the distant outer solar system, where it spent most of its time too far and too faint for surveys to notice. The asteroid's composition appeared unusually dark, reflecting only about 4% of sunlight, making it effectively invisible until very close to Earth. More concerning was 2019 OK's approach geometry. The asteroid arrived from the direction of the Sun, spending weeks in the daytime sky where optical telescopes cannot observe. Only during its final approach did it become visible to nighttime surveys. The case of 2020 QG pushed detection limits even further. This small asteroid, only 3 to 6 meters across, passed just 2,950 kilometers above Earth's surface on August 16, 2020, making it the closest known non-impacting asteroid ever recorded. The Zwicky Transient Facility spotted it 6 hours after closest approach. These discoveries reveal systematic biases in current detection methods. Ground-based optical surveys work best for objects approaching from directions away from the Sun, following predictable orbital paths and possessing surfaces bright enough to reflect significant sunlight. The problem becomes acute for objects on highly inclined orbits that approach Earth from above or below the plane of the solar system. Most surveys concentrate observations near the ecliptic, where the majority of asteroids travel. Objects approaching from high angles can remain undetected until very close. Weather compounds timing issues. Cloud cover can shut down optical observations for days or weeks, creating temporal gaps in sky coverage. Since many asteroids remain detectable for only brief periods, weather-related losses can mean the difference between detection and complete surprise. International cooperation helps fill some gaps by providing geographic diversity. When weather closes observatories in one hemisphere, facilities on the opposite side can continue surveys. However, the sunward detection problem affects all ground-based observatories equally. Despite these challenges, the statistical threat from undiscovered asteroids remains manageable. The objects most likely to escape detection are generally smaller asteroids that pose regional rather than global threats. For 2032, the detection bias analysis provides additional reassurance. The largest and most dangerous asteroids are also the easiest to detect, meaning our catalogues are most complete, precisely where completeness matters most for planetary defense. June 30th, 1908, 7:17 a.m. local time. Semyon Semenov was sitting on his cabin porch near the Podkamennaya Tunguska River in Siberia when the sky exploded. The sky split in two, and fire appeared high and wide over the forest, he later recalled. At that moment, I became so hot that I couldn't bear it, as if my shirt was on fire. Semenov was witnessing one of the most powerful natural explosions in recorded human history from 65 kilometers away. At ground zero, an area of forest larger than Greater London was flattened instantly, with 80 million trees knocked down in a radial pattern, visible from space decades later. The Tunguska event released energy equivalent to 1,000 Hiroshima-sized atomic bombs, roughly 15 megatons of TNT. The explosion was heard 800 kilometers away and created seismic waves that traveled around Earth twice. For several nights, residents of Europe and Western Asia reported unusually bright skies. What makes Tunguska particularly relevant to modern asteroid discussions is what wasn't found at the impact site. Despite massive explosion and widespread devastation, no crater existed. No meteorite fragments could be definitively identified. The forest was gone, but the ground showed no signs of high-velocity impact. The mystery deepened during the first scientific expedition in 1927, led by Soviet mineralogist Leonid Kulik. Expecting to find a massive crater and valuable meteorite fragments, Kulik instead discovered destruction unlike anything in scientific literature. Trees were flattened radially outward, but at the central point, some trees remained standing, stripped of branches and bark. Scientific consensus now holds that Tunguska was caused by an asteroid or comet, roughly 50 to 80 meters in diameter, that exploded in Earth's atmosphere at 8 to 10 kilometers altitude. The object was traveling at approximately 54,000 kilometers per hour when atmospheric pressure caused it to fragment and explode with tremendous force. This airburst scenario explains Tunguska's unique characteristics. The explosion's altitude meant most material was vaporized or scattered as tiny particles. Only microscopic traces reached the ground, mixed with natural debris and nearly impossible to identify. The lack of a crater reflected that no substantial mass survived to impact the surface. Tunguska represents the most recent large-scale asteroid impact in human history, providing crucial data about such events. The explosion created a distinctive butterfly pattern of treefall that has become a template for understanding atmospheric explosions. The event demonstrated the immense power in relatively modest-sized asteroids. An object perhaps 60 meters across, small enough to fit inside a city block, possessed enough energy to devastate a metropolitan region. If the same explosion had occurred over London or New York, instead of remote Siberian wilderness, millions would have died instantly. Statistical analysis suggests Tunguska-scale events occur roughly once every 300 to 1,000 years. Human civilization has been fortunate to experience only one such event in recorded history, occurring in one of Earth's most sparsely populated regions. For 2032 specifically, no known asteroid poses a Tunguska-level threat, and the probability of surprise impact by an undiscovered object remains extremely low. February 15th, 2013, 9:20 a.m. local time. Residents of Chelyabinsk, Russia, were beginning their Friday morning routines when the sky lit up brighter than the sun. A fireball streaked across the heavens, visible for hundreds of kilometers. Then came the shockwave. Windows shattered throughout the city. Buildings shook. Car alarms wailed. Over 1,000 people were injured, most by flying glass. The Chelyabinsk meteor was captured on hundreds of dashboard cameras throughout the region, providing unprecedented video documentation of a significant asteroid impact event. These recordings showed a brilliant white-hot fireball racing across the morning sky, leaving a persistent contrail that lingered for hours. Analysis revealed that the asteroid was approximately 20 meters in diameter and weighed roughly 13,000 tons before entering Earth's atmosphere. It approached from the sunward direction, making it effectively invisible to ground-based surveys until the moment of impact. The object fragmented multiple times during atmospheric entry. The explosion released energy equivalent to roughly 500,000 tons of TNT, making it the most powerful atmospheric explosion since nuclear weapons testing. Yet this immense release represented only a fraction of the asteroid's original kinetic energy. Most of the object's mass was vaporized during atmospheric passage. Recovery efforts found meteorite pieces scattered across a wide area, with the largest fragment weighing about 650 kilograms. Chemical analysis confirmed that the Chelyabinsk meteor was an ordinary chondrite, a common type of stony asteroid with composition similar to many objects in the asteroid belt. The injury toll highlighted an important aspect often unmentioned. Most casualties result from indirect effects rather than direct contact with the incoming object. Of the 1,491 people who sought medical attention, the vast majority were injured by flying glass from windows shattered by the explosion's shockwave. This pattern has profound implications for impact preparedness. Even relatively small asteroids can cause widespread injuries through structural damage and panic responses. The Chelyabinsk event demonstrated that proper building codes and emergency preparedness could significantly reduce casualties. The scientific windfall was unprecedented. For the first time, researchers had extensive video documentation of a significant asteroid impact from multiple angles. Seismographic stations recorded the shockwaves. Infrasound networks tracked atmospheric pressure waves. This wealth of data revolutionized understanding of atmospheric entry physics. Most sobering was the realization that Chelyabinsk-sized asteroids are both relatively common and largely undetectable by current surveys. Estimates suggest objects of similar size impact Earth roughly once every 50 to 100 years, but their small size and often sunward approaches make them nearly impossible to spot in advance. For planetary defense planning, Chelyabinsk represents a significant but manageable category of threat. Objects of this size cause regional damage but don't threaten civilization. The challenge lies in detection, since 20-meter asteroids often remain invisible until hours before impact. Looking toward 2032, the Chelyabinsk experience provides both caution and reassurance. While objects of similar size could certainly impact Earth in any given year, the probability that any specific location will be affected remains extremely low. 66 million years ago, life on Earth was thriving in ways that would seem alien to modern observers. Giant dinosaurs ruled terrestrial ecosystems, while marine reptiles dominated ancient seas. The climate was warm and humid, supporting lush forests that extended to polar latitudes. Then, in a geological instant, roughly 75% of all species vanished in the Cretaceous-Paleogene extinction event. The asteroid that triggered this mass extinction was nothing like the modest space rocks that occasionally threaten modern cities. This was a mountain-sized object, roughly 10 to 15 kilometers in diameter, traveling at approximately 72,000 kilometers per hour when it struck near what is now Mexico's Yucatan Peninsula. The impact created the Chicxulub crater, 180 kilometers across and 20 kilometers deep. The energy released by this collision defies comprehension. Conservative estimates place it at 100 million megatons of TNT, roughly 2 million times more powerful than the largest nuclear weapon ever tested. The impact instantly vaporized both the asteroid and enormous volumes of Earth's crust, launching debris clouds into space while digging a crater deeper than Mount Everest is tall. Within minutes, effects began cascading globally. Molten rock ejected by the explosion rained back down across the entire planet, heating the atmosphere to oven-like temperatures and igniting wildfires on every continent. The thermal pulse was so intense that any large animal exposed to open sky would have been killed by radiant heat alone. The longer-term effects proved even more devastating. Impact debris and soot from global wildfires blocked sunlight for months or years, plunging Earth into prolonged impact winter. Photosynthesis ceased across most of the planet, causing food webs to collapse from the bottom up. Temperatures dropped dramatically as solar energy failed to penetrate the debris-laden atmosphere. Chemical changes accompanied physical devastation. The impact vaporized sulfur-rich rocks at the crash site, injecting massive amounts of sulfur compounds into the atmosphere. These chemicals formed acid rain that poisoned freshwater ecosystems and acidified the oceans. Yet extinction wasn't instantaneous or complete. Fossil evidence suggests the dying process extended over thousands of years as ecosystems collapsed in complex cascades. Some species survived by virtue of size, habitat, or feeding strategies. Small mammals, birds, crocodiles, and many marine organisms managed to persist. The Chicxulub impact represents the most recent of several mass extinction events in Earth's history, but it's the only one for which we have clear evidence of an asteroid cause. The extinction demonstrates that cosmic impacts can literally reset evolution's direction. The ecological niches vacated by dinosaurs were eventually filled by mammals, leading to human civilization. For modern planetary defense, Chicxulub represents the ultimate nightmare, but also the most unlikely threat. Asteroids large enough to cause mass extinctions are extremely rare, with impacts occurring roughly once every 100 million years. Current surveys have catalogued virtually all asteroids in this size range, finding none on Earth-threatening trajectories. For 2032 specifically, the Chicxulub comparison offers complete reassurance. No known asteroid approaches even 1% of the size required for mass extinction effects. The comprehensive sky surveys of recent decades have effectively eliminated the possibility of surprise visits by civilization-ending asteroids. The first millisecond of a major asteroid impact contains more concentrated energy than humanity has ever witnessed. Picture a mountain-sized rock traveling 20 times faster than a rifle bullet, carrying kinetic energy equivalent to millions of nuclear weapons, suddenly encountering the immovable barrier of Earth's surface. The physics that unfold determine whether the impact creates a local crater or reshapes the entire planet. At contact, pressures exceed anything found in Earth's interior. The asteroid's leading edge experiences stress levels measured in millions of atmospheres, instantly vaporizing rock and metal into plasma hotter than the sun's surface. This vaporization occurs faster than sound can travel through solid material, creating shockwaves that propagate through both asteroid and target surface at hypersonic velocities. The shockwave compression transforms ordinary rock into exotic high-pressure materials that exist nowhere else on Earth's surface. Quartz crystals reorganize into shocked quartz with distinctive patterns that serve as fingerprints of impact events. New mineral phases appear that require pressures found only in Earth's deep mantle. Within the first second, the expanding shockwave has excavated a cavity many times larger than the original asteroid. The explosion behaves like a nuclear blast occurring underground, with shockwaves reflecting off the surface and creating complex interference patterns that determine final crater shape. Crater formation follows well-understood scaling relationships connecting impactor size to final crater diameter. A 1-kilometer asteroid typically creates a crater roughly 15 kilometers across, while a 10-kilometer impactor produces craters exceeding 100 kilometers in diameter. The excavation process ejects material in distinct phases with different velocity distributions. The fastest moving debris, launched during the initial shockwave, can achieve velocities of tens of kilometers per second, carrying impact signatures to locations thousands of kilometers away. Atmospheric effects become crucial for smaller impacts. Objects less than about 50 meters in diameter typically fragment during atmospheric entry, creating airburst explosions that release energy above ground level rather than at the surface. These atmospheric explosions can cause widespread damage without creating any crater. Ocean impacts present different physics but similar energy considerations. Water doesn't significantly slow down large asteroids, so ocean impacts still create explosive craters in the seafloor. However, displaced water generates tsunami waves that can cause coastal devastation far from the impact site. Global effects of major impacts result from debris interactions with Earth's atmosphere and climate system. Impact-generated dust can block sunlight for months or years, disrupting photosynthesis and causing temperature drops comparable to volcanic winters. Modern computational models can simulate impact processes with extraordinary detail, tracking physics from initial contact through long-term environmental effects. These simulations help predict consequences of potential future impacts and guide planetary defense planning efforts. For 2032, understanding impact anatomy provides reassurance that no known asteroid follows a trajectory that would subject Earth to any of these scenarios. Our knowledge of impact physics, derived from experiments and computer simulations, provides clear frameworks for assessing potential consequences, and for 2032, those frameworks consistently show zero significant threats. Earth bears the scars of cosmic violence across its entire surface, though most remain hidden beneath sediments, oceans, and relentless erosion. Unlike the Moon, whose crater-pocked face preserves a complete record of bombardment, Earth's active geology continuously reshapes the landscape, burying impact evidence beneath layers of newer rock. Yet careful geological detective work has revealed roughly 190 confirmed impact structures on Earth, ranging from small recent craters to ancient scars hundreds of kilometers across. Each represents a moment when cosmic debris found its way through Earth's atmospheric shield to reshape the landscape in violent, lasting ways. The most famous impact structure in North America is Meteor Crater in Arizona, a nearly perfect circular depression 1.2 kilometers across and 170 meters deep. Created roughly 50,000 years ago by an iron asteroid about 50 meters in diameter, this crater preserves classic features of a simple impact structure. The raised rim, composed of fractured and overturned rock layers, surrounds a bowl-shaped depression that remains clearly visible. Moving to larger scales, the Vredefort Dome in South Africa represents eroded remains of what was once the largest known impact structure on Earth. Created roughly 2 billion years ago by an asteroid perhaps 10 to 15 kilometers in diameter, the original crater may have been 300 kilometers across. Today, only the central uplift remains visible. The Sudbury Basin in Ontario tells a similar story of ancient catastrophe on an almost incomprehensible scale. This 1.8 billion-year-old structure was created by an impact that left a crater, originally 200 to 250 kilometers in diameter. The impact was so severe that it melted enormous volumes of crustal rock. More recent impact structures reveal how frequently Earth encounters substantial asteroids. The Bosom Twi crater in Ghana, formed roughly 1 million years ago, demonstrates that significant impacts occur on human-relevant timescales. The Lonar crater in India, created about 50,000 years ago, shows that multiple large impacts have occurred within modern human existence. Ocean impacts present particular challenges for investigation since seafloor sediments quickly bury impact structures, and tectonic processes eventually recycle oceanic crust. Statistical models suggest roughly 70% of asteroid impacts occur in marine environments, but very few submarine impact structures have been definitively identified. The Chesapeake Bay impact structure, buried beneath sediments on the US East Coast, provides a rare example of a well-documented marine impact. Created 35 million years ago by an asteroid roughly 3 kilometers in diameter. This buried crater spans 85 kilometers. Impact frequency analysis based on crater counts and astronomical observations suggests civilization-threatening impacts occur roughly once every 10,000 years, 100,000 to 1 million years, while regional scale events happen every few thousand years. These statistical estimates help contextualize asteroid risks compared to other natural disasters. The geological record also reveals that life on Earth has survived multiple major impact events. While the most severe impacts certainly caused extinctions and ecosystem disruptions, the overall pattern shows remarkable resilience in Earth's biosphere. For contemporary threat assessment, the geological record provides both perspective and reassurance. The scarred landscape confirms that major impacts do occur and cause significant environmental changes. However, the mathematical relationship between impact size and frequency demonstrates that truly catastrophic events remain rare on human timescales. Between the orbits of Mars and Jupiter, roughly 400 million kilometers from Earth, lies a vast ring of rocky debris that represents both the birthplace of most Earth-threatening asteroids and a graveyard of planetary formation gone wrong. The asteroid belt contains hundreds of thousands of objects larger than 1 kilometer, along with millions of smaller fragments, all following independent orbits in a gravitational dance that occasionally flings members toward the inner solar system. Despite science fiction depictions of dense asteroid fields, the belt is actually mostly empty space. The total mass of all asteroidal material equals roughly 4% of the Moon's mass, distributed across a volume billions of times larger than Earth. Spacecraft regularly traverse the belt without encountering a single rock. The belt's structure reflects Jupiter's gravitational influence, whose massive presence prevented the asteroid region from coalescing into a single planet during solar system formation. Instead, Jupiter's gravity created resonance zones where asteroid orbits become unstable, leading to collisions that fragment larger objects into smaller pieces. The Kirkwood gaps, regions within the belt where few asteroids are found, demonstrate Jupiter's ongoing influence. Objects orbiting in these gaps experience regular gravitational kicks from Jupiter that eventually alter their orbits enough to remove them from the belt entirely. Some of these ejected asteroids find their way into Earth-crossing orbits. The process of asteroid escape operates on million-year timescales through complex gravitational interactions. An asteroid might spend eons in a stable belt orbit before a collision nudges it slightly toward a Kirkwood gap. Once trapped, Jupiter's repeated gravitational influence gradually pumps up the orbit's eccentricity until it extends into the inner solar system. Different belt regions contain objects with distinctly different compositions, reflecting temperature gradients during solar system formation. Inner belt asteroids tend to be rocky and metallic, while outer belt objects often contain significant water ice and organic compounds. The largest asteroid, Ceres, has been reclassified as a dwarf planet due to its substantial size. With a diameter of 940 kilometers, Ceres contains roughly 1/3 of the belt's total mass and shows evidence of past geological activity. Its gravitational influence helps stabilize nearby asteroid orbits. Vesta, the second largest asteroid, displays evidence of differentiation into core, mantle, and crust structure similar to terrestrial planets. Meteorites found on Earth have been traced back to Vesta through spectroscopic analysis, proving that material can travel from the asteroid belt to our planet through natural processes. Near-Earth asteroids represent a continuously replenished population of belt escapees, with new objects arriving roughly as fast as existing ones are removed by planetary collisions or ejection from the solar system. This steady-state population means the near-Earth asteroid threat will persist for millions of years. Current astronomical surveys monitor belt asteroids to better understand population dynamics that control near-Earth object supply rates. By tracking how objects move between different orbital regions, scientists can predict future trends in the near-Earth asteroid population. For 2032 specifically, the belt connection provides additional reassurance about threat assessment accuracy. The known near-Earth asteroids originated through processes taking millions of years to complete. Their current orbits have been shaped by thoroughly understood gravitational interactions. The absence of 2032 threats among catalogued objects reflects real orbital dynamics rather than observational limitations. While optical telescopes strain to detect faint reflected sunlight from dark asteroids, there's another approach that turns the challenge inside out. Hunt them by their heat. Every object in space absorbs sunlight and re-radiates that energy as infrared radiation. This thermal emission provides detection regardless of surface brightness, revealing asteroids that might remain invisible to traditional surveys. The Near-Earth Object Wide Field Infrared Survey Explorer, known as NEOWISE, represents humanity's most successful infrared asteroid hunting mission. Originally launched as WISE in 2009 for an all-sky infrared survey, the spacecraft was repurposed for asteroid detection when its primary mission concluded. NEOWISE operates from Earth orbit, above atmospheric water vapor that blocks infrared radiation from reaching ground-based telescopes. From this vantage point, the spacecraft can detect thermal signatures against the cold background of space with impossible sensitivity for ground-based systems. The thermal detection method provides several advantages over optical surveys. An asteroid's infrared brightness depends primarily on its size and distance from the Sun, making it less sensitive to surface composition than reflected light observations. Dark asteroids that might escape optical detection appear prominently in infrared surveys. Since resuming operations in 2013, NEOWISE has discovered over 3,000 near-Earth objects, including more than 400 larger than 1 kilometer in diameter. These discoveries have significantly improved catalogue completeness for the largest and most dangerous asteroids. The spacecraft follows a sun-synchronous polar orbit that allows surveying the entire sky every 6 months, as Earth moves around the Sun. This orbital geometry provides multiple opportunities to detect objects and confirm their orbital characteristics. NEOWISE. Observations have revealed unexpected diversity in asteroid thermal properties. Some objects heat up and cool down quickly as they rotate, suggesting surfaces covered with fine dust that responds rapidly to changing solar illumination. Others show more gradual temperature variations, indicating solid rock surfaces or insulating layers. The mission has been particularly effective at finding large, dark asteroids that optical surveys tend to miss. These objects, with surfaces reflecting less than 5% of incident sunlight, can remain nearly invisible to ground-based telescopes until they approach very close to Earth. Combining NEOWISE infrared observations with optical data from ground-based surveys provides powerful synergies for asteroid characterization. The thermal measurements constrain object sizes and surface properties, while optical observations reveal composition and rotation details. The spacecraft's longevity has exceeded all expectations, continuing operations more than a decade after launch, despite being designed for a much shorter mission. Extended operations have allowed tracking seasonal and long-term changes in asteroid thermal properties. Data from NEOWISE has refined statistical estimates of the near-Earth asteroid population, particularly for objects larger than 1 kilometer. The thermal detection method provides more accurate size measurements than optical techniques, which must make assumptions about surface reflectivity. Future infrared missions, including the planned NEO Surveyor, will extend NEOWISE's capabilities with improved sensitivity and more sophisticated instrumentation. NEO Surveyor will operate at colder temperatures and longer wavelengths, allowing detection of smaller and more distant objects. For 2032 threat assessment, NEOWISE observations provide crucial confirmation that no large dark asteroids remain undiscovered on Earth-threatening trajectories. The mission's systematic thermal survey has revealed the largest near-Earth asteroids with high completeness, and none show any possibility of impacting Earth in 2032. Every clear night, automated telescopes capture millions of images of the star-filled sky. Within hours, sophisticated computer algorithms sift through this vast digital haystack, searching for the few needles that betray moving asteroids. This process represents one of the most successful applications of artificial intelligence to astronomy, transforming asteroid detection from occasional lucky finds to systematic industrial-scale surveys. The algorithmic challenge is deceptively simple to describe, but extraordinarily difficult to implement. Compare two images of the same sky region taken hours apart, identify objects that have moved between exposures, and distinguish real asteroids from thousands of artifacts that can mimic moving objects. Modern detection algorithms employ multiple layers of filtering to separate genuine asteroid detections from false alarms. The first stage identifies all objects that appear in one image but not another, creating candidate lists containing thousands of potential detections per night. Subsequent filters analyze motion patterns, brightness characteristics, and morphological properties. Machine learning techniques have revolutionized this filtering process, allowing computers to recognize patterns too subtle for human programmers to encode explicitly. Neural networks trained on millions of confirmed asteroid detections can identify subtle characteristics that distinguish real objects from instrumental artifacts. The Catalina Sky Survey's detection pipeline processes over 1,000 gigabytes of image data nightly, identifying typically 1,000 to 2,000 candidate moving objects for human review. The automated algorithms reduce this number from millions of initial detections to a manageable list that experienced observers can evaluate within hours. Human expertise remains crucial for final detection verification. Experienced asteroid hunters can recognize subtle patterns that even sophisticated algorithms miss, distinguishing between genuine discoveries and rare types of false alarms. The collaboration between automated detection and human judgment creates reliability that neither component could achieve alone. Quality control procedures ensure detection algorithms maintain consistent performance across different observing conditions and instrumental configurations. Regular injection of artificial moving objects into image data tests whether algorithms can reliably detect asteroids under various scenarios. Database management represents another crucial component of automated detection. Each survey maintains catalogs of millions of known objects with their predicted positions, allowing algorithms to distinguish between new discoveries and previously catalogued asteroids. International coordination ensures detection efforts don't duplicate each other unnecessarily. The Minor Planet Center serves as a global clearinghouse for asteroid observations, allowing surveys worldwide to share data and coordinate follow-up observations. Automated follow-up systems can now request additional observations of newly discovered objects without human intervention. These systems evaluate detection significance, predict optimal observation windows, and submit observation requests to appropriate telescopes. For 2032 threat assessment, the automated detection systems provide high confidence in catalog completeness. Algorithms running continuously for over a decade have systematically surveyed the accessible sky, identifying asteroids with consistent efficiency. The absence of 2032 threats in current catalogs reflects the thoroughness of these automated searches. Deep in the Mojave Desert, a massive 70-meter antenna dish tracks objects invisible to the naked eye, thousands of kilometers away in space. The Goldstone Deep Space Communications Complex doesn't just listen to signals from distant spacecraft, it also serves as humanity's most powerful asteroid radar system, capable of mapping surface features on near-Earth objects with resolution rivaling high-altitude reconnaissance aircraft. Planetary radar operates on principles fundamentally different from passive astronomical observation. Instead of waiting for objects to emit or reflect natural radiation, radar systems actively illuminate targets with powerful radio transmissions, then capture and analyze returning echoes. The Goldstone system can transmit up to 450 kilowatts of radio power in a tightly focused beam, creating the strongest radio signal ever directed at asteroids. When this energy reflects off an asteroid's surface, sensitive receivers capture returning radiation, which carries detailed information about the target's physical characteristics. Range measurements from radar echoes achieve extraordinary precision, often determining asteroid distances to within meters despite targets located millions of kilometers away. These measurements come from analyzing round-trip time for radio signals traveling at light speed. Doppler shift analysis reveals asteroid rotation rates and surface topology through frequency analysis of returning echoes. Different parts of a rotating asteroid move toward or away from Earth at slightly different velocities, creating frequency shifts that radar systems can measure with extreme precision. The Arecibo Observatory in Puerto Rico served as planetary radar's most sensitive receiver until its collapse in 2020. The combination of Goldstone's powerful transmitter and Arecibo's large collecting area created a bistatic radar system with capabilities exceeding what either facility could achieve alone. Goldstone radar observations have revealed surprising diversity in asteroid shapes, compositions, and structures. Some objects appear to be solid monoliths with relatively smooth surfaces, while others show evidence of being loose aggregations of smaller fragments held together by weak gravitational forces. The technique has discovered numerous binary asteroids, objects consisting of two or more components orbiting around their common center of mass. Roughly 15% of near-Earth asteroids larger than 200 meters appear to be binary or multiple systems. Radar characterization provides crucial information for assessing impact risks and deflection strategies. Solid metallic asteroids might survive atmospheric passage intact and create substantial craters, while loosely bound rubble piles could fragment into multiple smaller pieces. The radar technique works best for objects passing relatively close to Earth, typically within a few million kilometers. At greater distances, signal strength becomes too weak to provide detailed information, limiting radar observations to brief windows around closest approach. Greenbank Observatory in West Virginia has emerged as an important complement to Goldstone for planetary radar observations. While lacking Goldstone's powerful transmitter, Greenbank's large collecting area and advanced receivers make it highly effective for capturing radar echoes from asteroid targets. For 2032 threat assessment, radar observations provide definitive confirmation that catalogued near-Earth asteroids pose no impact risks. Objects approaching close enough for detailed radar mapping have been thoroughly characterized, revealing no threatening trajectories. On any clear night, thousands of dedicated amateur astronomers worldwide turn their backyard telescopes toward the stars, not just to admire cosmic scenery, but to contribute meaningful data to asteroid research. These citizen scientists, armed with modest equipment but boundless enthusiasm, form an essential component of the global asteroid tracking network. The democratization of asteroid detection began with the digital camera revolution that made sophisticated astronomical imaging accessible to amateur budgets. Modern CCD cameras costing less than professional telescope mounts from previous decades can detect asteroids too faint for visual observation. Tim Sparr, former director of the Minor Planet Center, once estimated that amateur astronomers contribute roughly 30% of all asteroid position measurements submitted for orbit calculation. This remarkable statistic reflects both the dedication of individual observers and the collective power of distributed observational networks. The geographic distribution of amateur observers provides crucial coverage gaps that professional surveys cannot fill economically. While major detection systems concentrate in locations with exceptional atmospheric conditions, amateur networks span every continent and time zone. Equipment requirements for meaningful amateur asteroid work have become surprisingly modest. A telescope with 20 to 30 centimeters aperture, a digital camera, and appropriate software can detect asteroids as faint as magnitude 18 or 19 under good conditions. The Asteroid Zoo Citizen Science Project exemplifies how technology can amplify amateur contributions. Participants examine telescope images online, marking objects that appear to move between successive exposures. The collective judgment of thousands of volunteers achieves detection reliability comparable to automated algorithms. Amateur discovery of near-Earth asteroids continues despite competition from automated professional surveys. Objects approaching from unusual directions, displaying atypical brightness patterns, or following highly eccentric orbits, sometimes escape initial detection by routine surveys. Photometry represents another crucial area of amateur contribution. Measuring asteroid brightness changes as objects rotate provides information about shape, composition, and rotation periods that complements position measurements for orbit calculation. The amateur asteroid community operates through informal networks that share observing plans, distribute target lists, and coordinate follow-up observations. Online forums and email lists connect observers worldwide, allowing rapid communication about new discoveries and urgent follow-up needs. Astrometric precision from amateur observations has improved dramatically as digital cameras replace photographic plates, and GPS time synchronization eliminates timing errors. Modern amateur position measurements routinely achieve accuracy within 1 arcsecond, meeting professional standards for orbit calculation. Advanced amateur facilities increasingly rival professional capabilities for specific research applications. Large private observatories equipped with meter-class telescopes and sophisticated instrumentation can conduct asteroid research at levels matching university facilities. The COVID-19 pandemic demonstrated the resilience of amateur observing networks compared to professional facilities. While many observatories suspended operations due to travel restrictions, amateur observers continued working from their home facilities, maintaining continuity in asteroid tracking. Specialized amateur contributions include occultation observations, where asteroids pass in front of background stars. These rare events provide precise measurements of asteroid sizes and shapes that no other technique can achieve. For 2032 threat assessment, the amateur observing community provides independent confirmation of professional survey completeness. The absence of amateur discoveries showing threatening 2032 trajectories supports confidence in current threat assessments. On rare occasions, cosmic geometry aligns to create one of astronomy's most precise measurement opportunities, a stellar occultation, when an asteroid passes directly between Earth and a background star. For anywhere from milliseconds to several minutes, the star's light disappears as the asteroid's solid body blocks the stellar disk. These brief eclipse events provide extraordinarily precise measurements of asteroid sizes and shapes. Predicting occultations requires precise knowledge of both asteroid orbits and stellar positions. Astronomers must calculate exactly when and where an asteroid's shadow will sweep across Earth's surface, creating a narrow path of visibility, typically only a few dozen kilometers wide. The International Occultation Timing Association coordinates global networks of observers who position themselves along predicted shadow paths, equipped with telescopes, high-speed cameras, and GPS timing systems. When successful, these observations capture the exact moments when starlight disappears and reappears. Multiple observers distributed across the shadow path can reconstruct the asteroid's silhouette by combining their individual timing measurements. Each observer records when the star disappeared and reappeared from their specific geographic location, providing 2 data points that define the asteroid's edges. The technique has revealed remarkable diversity in asteroid morphologies. Some objects appear nearly spherical, consistent with gravitational shaping in larger asteroids. Others show highly irregular outlines suggesting fragmented or contact binary structures. Occultation observations provide the most accurate, direct measurements of asteroid sizes available to ground-based astronomy. Unlike radar ranging or thermal modeling, occultations measure physical cross-sections directly. The accuracy often exceeds measurements from spacecraft flybys conducted at much greater cost. Recent technological advances have transformed occultation observations from challenging visual timing exercises to routine digital video recordings. Modern cameras can record stellar brightness changes with millisecond time resolution, while GPS receivers provide precise timing references. The European Space Agency's Gaia mission has revolutionized occultation predictions by providing extraordinarily precise stellar positions. Previous predictions relied on star catalogues with positional uncertainties, that often made occultation paths uncertain by hundreds of kilometers. Gaia's microarc-second astrometry has reduced these uncertainties to just a few kilometers. Atmospheric effects can complicate occultation observations, particularly for events involving small asteroids or faint stars. Earth's turbulent atmosphere causes stellar positions to wander slightly, potentially masking brief occultations or creating false signals. Some occultations reveal unexpected asteroid properties that other techniques cannot detect. Observations sometimes show gradual brightness changes rather than sharp disappearances, indicating rough surface topography or loose debris clouds surrounding solid nuclei. The citizen science aspects of occultation observations demonstrate the continued importance of amateur contributions to professional astronomy. Many successful observations come from dedicated amateurs who travel hundreds of kilometers to position themselves within narrow shadow paths. Rare grazing occultations, where asteroids pass near star edges rather than directly in front, can provide information about surface roughness and topography. These events produce complex brightness patterns as starlight passes between surface irregularities. Future all-sky surveys will dramatically increase occultation opportunities by cataloguing millions of additional asteroids and billions of stars to unprecedented precision. The Vera Rubin Observatory's Legacy Survey will discover hundreds of thousands of new asteroids, while providing precise astrometry for occultation predictions. For 2032 asteroid threat assessment, occultation observations provide independent validation of asteroid sizes estimated through other methods. The technique's precision ensures that size-dependent impact risk calculations rest on solid observational foundations. Every few months, somewhere in the global asteroid detection network, a newly discovered object triggers automated risk assessment algorithms that flag a small but measurable probability of Earth impact. These initial threat notifications often generate brief media attention and public concern before follow-up observations eliminate the apparent danger. While these false alarms can cause unnecessary anxiety, they serve crucial roles in testing planetary defense procedures. The anatomy of a typical false alarm begins with discovery observations that provide only limited information about an asteroid's trajectory. Initial orbital calculations based on a few position measurements often show large uncertainties that can include Earth-intersecting paths. Asteroid 2004 MN4, later named Apophis, provides the most dramatic example of how false alarms unfold and resolve. Initial orbital calculations placed this 370-meter asteroid on a trajectory with a 1 in 37 chance of striking Earth on April 13, 2029. The object briefly reached level 4 on the Torino scale, the highest rating ever assigned. Only months of additional observations conclusively eliminated the impact possibility. The 2017 discovery of asteroid 2017 VL2 demonstrated how quickly false alarms can be resolved with modern follow-up capabilities. Initial calculations suggested a small possibility of impact in 2018. But observations from multiple telescopes within days refined the orbit enough to eliminate any threat. Communication challenges during false alarms reflect tensions between scientific accuracy and public understanding. Astronomers must convey that initial impact probabilities, while mathematically valid given limited data, almost always decrease to zero with additional observations. The Torino scale was specifically designed to address communication challenges by providing a color-coded framework similar to hurricane categories. Objects rated 0 or 1 pose no immediate concern and should not generate public alerts. Ratings of 2 or higher indicate objects deserving attention from both astronomers and the public. Automated early warning systems must balance sensitivity against false alarm rates. Overly sensitive systems generate frequent false alerts that can overwhelm follow-up resources and create alert fatigue among both astronomers and the public. Follow-up observation networks have evolved to respond rapidly to potential threats identified by survey systems. Automated alerts can trigger coordinated observation campaigns within hours of initial detection, often resolving apparent threats before they generate significant public concern. The psychological impacts of false alarms extend beyond immediate public concern to longer-term attitudes about asteroid threats. Repeated false alarms can generate either complacency or chronic anxiety. Effective communication strategies must address both reactions while maintaining appropriate awareness levels. International protocols for sharing information about potential threats help prevent conflicting messages during false alarm situations. The International Astronomical Union coordinates communication through established channels, ensuring that threat assessments from different organizations remain consistent. Educational opportunities during false alarms can improve public understanding of how asteroid threat assessment actually works. These events provide natural teaching moments for explaining orbital mechanics, observational uncertainties, and the scientific process of hypothesis testing. The database of false alarms provides valuable information for improving threat assessment procedures. Statistical analysis of how initial impact probabilities change with additional observations helps calibrate uncertainty estimates for future discoveries. For 2032 threat assessment, the history of false alarms provides confidence in current procedures for eliminating apparent threats through additional observations. The rapid resolution of past false alarms demonstrates that the combination of improved telescopes, better software, and coordinated follow-up can quickly distinguish between genuine threats and observational uncertainties. September 26, 2022, 23:14 UTC. In a distant corner of space, humanity delivered its first intentional blow against a celestial adversary. The double asteroid redirection test, known simply as DART, struck the asteroid moon Dimorphos at 24,000 km per hour, instantly vaporizing the 570-kilogram spacecraft and creating a crater roughly 150 meters across. In that moment, planetary defense transitioned from theoretical possibility to demonstrated reality. DART's target was carefully chosen to maximize scientific return while minimizing Earth risk. Dimorphos orbits the larger asteroid Didymos in a binary system that poses no threat to our planet. The 160-meter diameter moon provided a perfect test case, large enough to survive impact without complete disruption, yet small enough that a modest spacecraft could measurably alter its orbit. The kinetic impactor concept underlying DART relies on straightforward physics, momentum transfer through high-velocity collision. When DART struck Dimorphos, Newton's laws required that momentum lost by the spacecraft be gained by the asteroid. The challenge lay in predicting exactly how much orbital change would result. Pre-impact predictions suggested that DART would change Dimorphos's orbital period around Didymos by roughly 10 minutes, shortening the 11-hour and 55-minute orbit to approximately 11 hours and 45 minutes. This seemingly modest change represented a significant alteration in celestial mechanics terms. The actual impact exceeded all expectations. Within days, ground-based observations confirmed that Dimorphos's orbital period had decreased by 32 minutes, more than 3 times the minimum change needed to declare mission success. The enhanced momentum transfer likely resulted from debris ejected during impact, which acted like a slow-motion explosion. High-speed cameras aboard DART captured the final approach moments, revealing Dimorphos's surface in unprecedented detail. The images showed a rubble pile structure composed of boulders and loose debris, rather than solid rock. This loose composition may have contributed to the unexpectedly large momentum transfer. The Italian Space Agency's Licia cube, deployed from DART shortly before impact, provided the only direct visual confirmation of the collision's immediate aftermath. This small CubeSat witnessed dramatic brightening and the formation of debris plumes extending thousands of kilometers from the impact site. Ground-based telescopes worldwide coordinated observations of the impact aftermath, tracking both the orbital period change and the evolving debris cloud. The Hubble Space Telescope captured detailed images of expanding debris trails that resembled comet tails. The momentum enhancement factor, representing how much additional momentum transfer resulted from impact ejecta compared to the spacecraft alone, emerged as a crucial parameter for future deflection planning. DART's factor of approximately 3.6 significantly exceeded conservative estimates. International cooperation in DART observations demonstrated global commitment to planetary defense research. Observatories in North America, South America, Europe, Africa, and Australia contributed measurements that provided comprehensive coverage. The European Space Agency's Hera mission, scheduled to reach the Didymos system in 2026, will provide detailed post-impact assessment. Hera will map the impact crater, measure changes in Dimorphos's shape and structure, and characterize debris distribution around both asteroids. DART's success validated computer models used for predicting deflection outcomes, while revealing areas where theoretical understanding needs improvement. The larger-than-expected momentum enhancement factor suggests that impact modeling must better account for ejecta production and debris interactions. For 2032 threat assessment, DART's success provides ultimate reassurance that technological solutions exist if any unexpected asteroid threats were discovered. The demonstrated ability to alter asteroid orbits, combined with comprehensive sky surveys showing no 2032 threats, creates multiple layers of protection against cosmic impacts. Humanity now possesses multiple proven methods for altering asteroid trajectories, each suited to different scenarios involving object size, composition, advance warning time, and mission constraints. The deflection toolbox represents decades of theoretical development validated by the DART mission's success, providing confidence that technological solutions exist for virtually any asteroid threat with sufficient advance warning. Kinetic impactors, demonstrated successfully by DART, work by ramming spacecraft into asteroids at high velocity to transfer momentum through collision. This brute force approach requires no exotic technology, relying instead on conventional spacecraft propulsion and navigation systems. The method works best for solid asteroids, where impact energy can be efficiently converted into orbital velocity changes. The effectiveness scales with both spacecraft mass and impact velocity, following fundamental momentum transfer physics. Larger deflection requirements demand either more massive impactors or higher collision velocities. Multiple smaller impacts, distributed over time, can achieve the same total momentum change as single large impacts while reducing fragmentation risk. Gravity tractors represent a gentler approach, using gravitational attraction between a spacecraft and asteroid to gradually alter trajectories over years or decades. A robotic probe stations itself near the target asteroid, using ion propulsion to maintain position, while its gravitational field slowly pulls the asteroid onto a modified orbit. The gravitational deflection approach demands exceptional precision in spacecraft navigation and station keeping, since the gravitational forces involved are extremely weak. However, gravity tractors offer precise control over deflection magnitude and direction, making them ideal for fine-tuning trajectories when impact timing must be adjusted with extraordinary accuracy. Nuclear explosive deflection represents the most powerful option, capable of handling the largest asteroids or scenarios with minimal advance warning. Nuclear devices could either detonate near asteroid surfaces to vaporize material and create thrust, or explode at safe distances to push targets through radiation pressure. Standoff nuclear explosions work by converting bomb energy into X-rays that vaporize thin layers of asteroid surface material. The expanding vapor cloud creates thrust that pushes the asteroid in the opposite direction. Computer simulations suggest this approach could deflect even kilometer-sized asteroids with single explosions. Solar sails attached to asteroids could provide continuous deflection force over long time periods using radiation pressure from sunlight. Large reflective surfaces deployed on asteroid surfaces would experience gentle but persistent thrust that accumulates over years or decades. Mass driver systems could achieve deflection by using electromagnetic railguns to launch asteroid material into space at high velocity. The reaction force from these launches would gradually accelerate the asteroid in the opposite direction. This method essentially converts asteroid mass into propulsion. Laser ablation deflection involves using powerful space-based laser systems to vaporize asteroid surface material, creating thrust through the same principles as ion beam shepherding, but with much higher power density. Ground-based laser arrays could potentially deflect small asteroids. The choice between deflection methods depends critically on advance warning time, since gentle techniques like gravity tractors require years or decades to accumulate meaningful trajectory changes, while kinetic impactors or nuclear options can work with shorter warning periods. Mission architecture considerations include spacecraft design, propulsion requirements, navigation accuracy, and international coordination. Multiple smaller deflection attempts distributed over time might prove more effective than single large missions. Risk assessment for deflection attempts must consider potential failure modes, including mission failures that leave threats unaddressed, partial deflections that delay impacts without preventing them, and fragmentation scenarios that create multiple smaller threats. For 2032 scenarios, the existence of proven deflection technologies provides ultimate reassurance that technical solutions exist for any unexpected discoveries. While no threats currently exist for that year, the demonstrated capabilities give confidence that future asteroid discoveries could be addressed through appropriate deflection methods. The future of asteroid detection promises to transform our current capability from finding most dangerous objects to cataloging virtually everything larger than a house that approaches Earth's neighborhood. Next-generation survey systems will achieve this revolutionary improvement through space-based infrared telescopes, unprecedented ground-based sensitivity, and artificial intelligence systems capable of processing data streams that would overwhelm current analysis capabilities. The NEO Surveyor mission, scheduled for launch in 2026, represents the next major leap in space-based asteroid detection. This infrared telescope will operate from a gravitationally stable orbit 1.5 million kilometers from Earth, providing continuous sky coverage without atmospheric interference. The mission's primary goal is completing the catalogue of objects larger than 140 meters in diameter. NEO, Surveyor's infrared detection capability, will find dark asteroids that optical surveys tend to miss, addressing a major gap in current catalogues. The mission's thermal sensitivity will detect objects regardless of their surface reflectivity, since all asteroids glow in infrared wavelengths due to solar heating. The Vera Rubin Observatory, beginning operations in 2025, will revolutionize ground-based asteroid detection through its unprecedented combination of field of view, sensitivity, and survey speed. The facility's 8.4-meter primary mirror and 3.2 gigapixel camera will capture more detail in single exposures than current surveys achieve in entire nights. Rubin Observatory's moving object detection capabilities will discover an estimated 5 million asteroids during its 10-year survey, increasing the known population by more than an order of magnitude. The survey will be particularly effective at finding objects in the outer solar system before they swing close to Earth. Machine learning algorithms will play increasingly important roles in processing enormous data streams from next-generation surveys. Artificial intelligence systems can identify subtle patterns in asteroid motion and brightness that might escape human attention, while filtering out vast numbers of false detections. Automated follow-up systems will coordinate observations from multiple telescopes to rapidly confirm new discoveries and refine orbital calculations. When one survey detects a potentially interesting object, automated software can immediately request confirmatory observations from other facilities worldwide. International coordination of next-generation detection systems will create unprecedented global coverage. Space-based infrared surveys complement ground-based optical detection, while southern and northern hemisphere facilities provide complete sky coverage. The sensitivity improvements will enable detection of smaller asteroids at greater distances, dramatically extending advance warning time for potential impacts. Objects that current surveys might detect only weeks before close approach will be found years or decades earlier. Statistical completeness goals will shift from focusing on civilization-ending threats to addressing regional-scale impacts that could affect millions of people. While current surveys have found most objects capable of causing global catastrophe, next-generation systems will catalogue the much more numerous population of city-killer asteroids. Space situational awareness networks will integrate asteroid detection with tracking of artificial satellites and space debris, creating comprehensive catalogues of all objects in Earth's vicinity. These integrated systems will improve collision avoidance for both natural and artificial objects. Planetary Defense Coordination Centers will synthesize data from multiple detection systems to provide comprehensive threat assessments and coordinate international responses to discovered hazards. These centers will maintain real-time awareness of all known near-Earth objects. For immediate planetary defense applications, next-generation detection systems will provide definitive answers about impact threats decades into the future. The combination of space-based infrared surveys, ground-based optical detection, and sophisticated data processing will achieve catalog completeness levels that eliminate uncertainty about major asteroid threats well beyond 2032. Asteroid impacts recognize no national boundaries, making planetary defense one of the few challenges that genuinely requires global cooperation for effective response. Unlike climate change or pandemics that affect different regions with varying intensity, a significant asteroid impact would instantly become everyone's problem. This shared vulnerability has fostered unprecedented international collaboration in asteroid detection and deflection planning. The United Nations Office for Outer Space Affairs coordinates international planetary defense efforts through its Committee on the Peaceful Uses of Outer Space. This committee provides the primary forum for developing international agreements on asteroid threat response, establishing protocols for sharing observational data and coordinating deflection missions. The International Asteroid Warning Network, established in 2013, creates formal channels for sharing information about newly discovered asteroid threats. When any member organization detects a potentially hazardous object, standardized notification procedures ensure that relevant information reaches all participating space agencies and research institutions within hours. Space agency partnerships have evolved from informal cooperation to formal agreements covering asteroid research and planetary defense activities. NASA collaborates closely with ESA, JAXA, Roscosmos, and other agencies on asteroid missions, data sharing, and technology development. The European Space Agency's Space Situational Awareness Programme exemplifies international cooperation by providing asteroid tracking services to nations lacking comprehensive detection capabilities. European telescopes and computational resources support global planetary defense efforts while sharing data freely with international partners. Legal frameworks for international asteroid deflection remain underdeveloped, creating potential complications if rapid response becomes necessary. The Outer Space Treaty prohibits weapons of mass destruction in space, but doesn't explicitly address nuclear deflection of asteroids. Decision-making authority for deflection missions presents complex challenges when impacts might affect some regions more than others. An asteroid approaching Earth along a trajectory that threatens Asia might cause minimal damage to the Americas, creating potential conflicts between global benefit and regional costs. The International Astronomical Union's Minor Planets Center serves as the global clearinghouse for asteroid observations, processing data from observatories worldwide and maintaining authoritative catalogues of known objects. This centralized approach prevents conflicting orbit calculations and ensures that threat assessments rest on complete observational data. Technology sharing agreements facilitate international collaboration on deflection system development while addressing national security concerns about sensitive technologies. Kinetic impactor systems share significant technology with military applications, while nuclear deflection methods involve weapons-grade materials and designs. Financial responsibility for planetary defense activities raises questions about cost distribution among nations with vastly different economic capabilities. Should deflection mission costs be shared equally, proportional to GDP, or based on regional impact risks? Regional space agencies and emerging space nations contribute increasingly to global planetary defense efforts through ground-based observations, data analysis, and specialized research capabilities. Countries with limited space infrastructure can still make valuable contributions through geographic diversity in observation networks. Crisis communication during asteroid emergencies will test international cooperation mechanisms under extreme stress. The combination of technical complexity, time pressure, and global media attention could strain diplomatic processes designed for less urgent circumstances. Public communication coordination prevents conflicting messages from different national authorities that might confuse or panic global audiences during asteroid emergencies. International agreements on public communication responsibilities ensure that authoritative information comes from recognized sources. Scientific collaboration extends beyond immediate planetary defense to fundamental research on asteroid formation, evolution, and population characteristics. International research partnerships advance basic understanding of asteroid populations while developing technologies that might prove crucial for future deflection missions. Looking toward 2032 and beyond, international cooperation mechanisms provide confidence that coordinated global response capabilities exist if unexpected asteroid threats emerge. The established networks for data sharing, technical cooperation, and diplomatic coordination create frameworks for rapid response that would be impossible to develop during actual emergencies. While 2032 shows no asteroid threats in current catalogues, the decades beyond present several objects that warrant careful monitoring due to small but measurable impact probabilities decades into the future. These long-term threats illustrate both the precision of modern orbital calculations and the challenges of predicting asteroid behavior across century-long timescales, where subtle effects can accumulate into significant trajectory changes. Asteroid 101955 Bennu, target of NASA's OSIR-ISREX sample return mission, holds a 1 in 2,700 chance of impacting Earth sometime between 2017-5 and 2019-9. This 490-meter diameter object follows an orbit that brings it close to Earth every 6 years, with each encounter slightly altering its trajectory through gravitational interaction. The Bennu impact scenario demonstrates how small gravitational perturbations can accumulate into large trajectory changes over century-long timescales. Each close approach to Earth deflects Bennu's orbit by small amounts that depend precisely on the asteroid's position at closest approach. Tiny differences in timing or distance get amplified through subsequent encounters. Advanced computer simulations track thousands of possible trajectories for Bennu, accounting for gravitational influences from all major solar system bodies, relativistic effects, solar radiation pressure, and the Yarkovsky effect that causes asteroids to drift slowly due to thermal emission. The OSIRIS-REx mission's detailed study of Bennu provides crucial data for refining long-term trajectory predictions. Precise measurements of the asteroid's mass, shape, rotation, and surface properties allow more accurate modeling of how various forces affect its motion. Several other asteroids show small but measurable impact probabilities in the late 21st and 22nd centuries. Asteroid 1950 DA has a 1 in 8,300 chance of striking Earth on March 16, 2080, making it the highest probability long-term threat currently known. Uncertainty growth in long-term orbital predictions reflects the chaotic nature of multibody gravitational dynamics. Small errors in current position or velocity measurements get amplified exponentially over time through repeated gravitational encounters. This mathematical chaos places fundamental limits on how far into the future asteroid trajectories can be predicted. The Yarkovsky effect introduces additional complexity by creating forces that depend on asteroid surface properties and rotation states. As asteroids absorb sunlight and re-radiate it as heat, the thermal emission creates tiny thrust forces that gradually alter orbits over millions of years. Planetary close encounters create the greatest sources of uncertainty in long-term asteroid trajectories. When objects pass near massive planets like Jupiter or Earth, small differences in approach geometry can result in dramatically different departure trajectories. Statistical impact assessment methods account for trajectory uncertainties by running thousands of numerical simulations with slightly different initial conditions. Each simulation follows one possible trajectory through future gravitational encounters, with the ensemble providing probability estimates for various outcomes. Collision monitoring systems continuously update impact probabilities as new observations refine orbital parameters. Objects that initially showed concerning long-term impact possibilities often see their threat probabilities reduced to zero, as more precise observations eliminate Earth-intersecting trajectories. The time horizons involved in long-term impact predictions exceed typical human planning cycles by orders of magnitude. Assessing threats that might materialize in 2175 or 2880 requires thinking about civilizational timescales rather than political or economic cycles. Deflection mission planning for long-term threats faces unique challenges related to timing and technology development. Missions to deflect asteroids like Bennu might need to launch decades before predicted impacts to allow sufficient time for trajectory changes to accumulate. International coordination for long-term threats involves additional complexities compared to immediate asteroid dangers. Political systems, space agencies, and international agreements may change dramatically over the decades between threat identification and required response. Risk communication for long-term threats must balance scientific accuracy with public understanding of probability and uncertainty. Explaining 1 in 2,700 chances of impact occurring 150 years in the future requires careful attention to how people interpret statistical information. The transition from 2032's clear skies to longer-term uncertainties illustrates both the success of current asteroid detection efforts and the ongoing challenges of planetary defense planning. While we can confidently state that 2032 poses no significant asteroid threats, the decades beyond require continued vigilance and preparation. As darkness falls and you settle into peaceful rest, a remarkable network of technology and human dedication maintains its vigilant watch over the cosmic neighborhood surrounding our small blue planet. Tonight, while you sleep, automated telescopes will photograph millions of stars. Computer algorithms will analyze thousands of images for signs of moving objects. And dedicated astronomers will evaluate potential discoveries that could affect everyone on Earth. The Catalina Sky Survey's robotic telescope high in the Arizona mountains will spend the dark hours systematically photographing patches of sky, each image capturing light that has traveled for years from distant stars. Sophisticated cameras cooled to temperatures far below freezing will detect asteroids too faint for human eyes to see, while computers will process the data in real time. Halfway around the world, the Neowise spacecraft orbits silently above Earth's atmosphere, its infrared sensors detecting the gentle heat radiated by asteroids warmed by sunlight. From its unique vantage point in space, NEOWISE can find dark objects that ground-based telescopes might miss. The mathematical precision underlying this cosmic surveillance provides profound reassurance about 2032's safety. Orbital mechanics operates according to laws as reliable as sunrise, allowing astronomers to predict asteroid positions decades into the future with extraordinary accuracy. The absence of threatening objects in current catalogues reflects real physical reality. Statistical analysis confirms that significant asteroid impacts remain rare events on human timescales. The relationship between asteroid size and impact frequency means that civilization-threatening events occur roughly once per million years, while regional-scale impacts happen perhaps once per 1,000 years. The successful DART mission has proven that humanity possesses the technological capability to alter asteroid trajectories when necessary. The dramatic success of this first planetary defense test, which changed an asteroid's orbit by more than 3 times the minimum required amount, demonstrates that deflection technology works even better than conservative estimates predicted. International cooperation in planetary defense continues strengthening as more nations recognize the shared nature of asteroid threats. The established networks for data sharing observation coordination, and mission planning create frameworks for rapid response should unexpected discoveries require deflection efforts. The amateur astronomy community provides additional layers of protection through thousands of dedicated observers who contribute meaningful data to professional asteroid research. These citizen scientists ensure that asteroid detection truly represents a global effort rather than the work of a few isolated institutions. Quality control procedures embedded throughout the detection and analysis process prevent false alarms while ensuring that genuine threats receive appropriate attention. The combination of automated detection, human verification, and independent confirmation creates multiple safeguards. The geological record provides historical perspective on impact frequencies and environmental effects that calibrates our understanding of asteroid risks. Earth's scarred surface tells the story of billions of years of cosmic bombardment, revealing that major impacts do occur but remain rare enough that advanced civilizations can develop effective defenses. Looking beyond 2032, the next generation of detection systems will achieve unprecedented completeness in cataloging potentially threatening asteroids. The NEO Surveyor Infrared Space Telescope and Vera Rubin Observatory will discover hundreds of thousands of additional asteroids. As you drift into peaceful sleep, the cosmic perspective provides its own form of comfort. We live in a universe vast beyond imagination, filled with wonders that inspire curiosity rather than fear. The same space that occasionally sends small visitors to light up our night skies as shooting stars also provides the vast distances that make dangerous encounters extraordinarily rare. The combination of rigorous science, advanced technology, and international cooperation has transformed asteroid impacts from unpredictable catastrophes to manageable risks. We can sleep soundly, knowing that dedicated people and sophisticated systems maintain constant vigilance against cosmic threats, while the laws of physics ensure that dangerous encounters remain rare enough for civilization to thrive. Tonight, the stars shine down on a world better protected from cosmic threats than any previous generation could have imagined. The question of whether an asteroid will hit Earth in 2032 has a clear, scientifically supported answer. No known object poses such a threat. This conclusion rests on solid observational evidence, sophisticated mathematical analysis, and comprehensive surveys. Sweet dreams under the cosmic skies, where ancient starlight carries messages of wonder rather than warning, and where human ingenuity has learned to read the gravitational signatures that keep our world safe from the wandering debris of deep space.